Biomolecules begin with one simple idea. Life is built from chemistry. But chemistry alone does not explain life. What matters is how a molecule behaves in a living system. This chapter starts with carbohydrates, then moves into classification, glucose, and finally the deeper question: why glucose behaves the way it does in reactions and structure? That sequence is the whole backbone of this part. Biomolecule. Everything in biology is made from non-living atoms. Yet, living systems grow, sustain themselves, and reproduce. That is the first mental shift. Biomolecules are the bridge between raw matter and life. The four major classes are carbohydrates, proteins, nucleic acids, and lipids. Carbohydrates are usually the first entry point because they are central to energy, structure, and storage. The old definition of carbohydrates as hydrates of carbon is historically important, but it is not reliable enough for modern chemistry. The better definition is that carbohydrates are optically active polyhydroxyaldehydes or ketones. Rhamnose is the classic outlier here. It does not match the hydrate formula neatly, but it is still a carbohydrate. Carbohydrates are classified by size. Monosaccharides cannot be split further and include glucose, fructose, and ribose. Oligosaccharides yield 2 to 10 units on cleavage. Sucrose and maltose are the standard examples. Polysaccharides yield a large number of units and are generally non-sweet, with starch, cellulose, and glycogen as the key names. This is where many students mix sweetness with structure. Do not. Sweetness is not the classification principle. The number of units is. A reducing sugar is one that can reduce failing solution or Tollens reagent. All monosaccharides are reducing sugars, whether they are aldoses or ketoses. Non-reducing sugars include many polysaccharides and specific disaccharides like sucrose. The practical shortcut is excellent. If it is a single ring monosaccharide, it almost always reduces. That saves time in exam conditions. Monosaccharides are classified first by carbon count and then by functional group. A triose has 3 carbons. A dextrose has 4. A pentose has 5. A hexose has 6. And a heptose has 7. Then comes the aldehyde or ketone distinction. Glucose is a 6-carbon sugar with an aldehyde group, so it is an aldohexose. That single label is enough to place it correctly in the entire monosaccharide family. Glucose is known by several names, including dextrose. It is the monomer of starch and cellulose, and it is one of the most abundant organic compounds on Earth. The slide also separates laboratory and commercial preparation. In the lab, sucrose with dilute HCl or H2SO4 in alcohol and heat gives glucose and fructose. On the commercial scale, starch or cellulose with dilute H2SO4 gives N-glucose. A detail students often miss is the extraction condition. The commercial process needs about 393 Kelvin and 2 to 3 atmospheres. The structure of glucose is supported by evidence. Prolonged heating with HI gives N-hexane, which proves that all 6 carbons are locked in a straight chain. Then glucose reacts with NH2OH to form an oxime and with HCN to form a cyanohydrin, proving that a carbonyl group is present. This is how chemistry builds confidence in structure. Chain evidence first, functional group evidence next. The next round of evidence comes from oxidation and derivatization. Mild oxidation with bromine water gives gluconic acid, which shows the carbonyl is an aldehyde group. Strong oxidation with nitric acid gives saccharic acid, confirming a primary alcohol group at the bottom as well. Acetylation with acetic anhydride gives glucose pentaacetate, which proves that 5 distinct hydroxyl groups exist. The key pattern is simple. Bromine water oxidizes only the top, while nitric acid oxidizes both top and bottom. The Fischer projection is where many students lose marks because they misplace the hydroxyl groups. For D plus glucose, the OH on carbon 3 is on the left, while the other chiral centers have their dash OH groups on the right. The shortcut given is worth remembering exactly in thought. C2 to C5 hydroxyl positions go right, left, right, right. That sequence is the cleanest way to reconstruct the Fischer projection in an exam. D and L configuration has nothing to do with optical rotation. That is a classic trap. It is purely about spatial arrangement relative to glyceraldehyde. The rule is straightforward. Identify the lowest asymmetric carbon, which is C5 in glucose. If the dash OH is on the right, it is D configuration. If the dash OH is on the left, it is L configuration. The slide uses D plus glyceraldehyde and D plus glucose to reinforce that D does not mean dextrorotatory by definition. The open chain structure of glucose looks neat, but it cannot explain all of glucose's behavior. A free aldehyde group should give standard aldehyde tests, yet glucose does not fully behave that way. It fails Schiff's test, does not form the NaHSO3 addition product, and its pentaacetate refuses to react with hydroxylamine. It also exists in 2 crystalline forms, alpha and beta. The conclusion is important. The open chain blueprint is incomplete. Something is hidden. That hidden form is the cyclic Haworth structure. The OH on carbon 5 reacts with the CHO on carbon 1 to form a stable 6-membered ring. Once that ring forms, the aldehyde group is locked up, which explains why Schiff's and NaHSO3 tests fail. The new carbon 1 becomes a new asymmetric center, and that creates alpha and beta isomers. Here's the term that students must hold tightly. Carbon 1 in the cyclic form is called the anomeric carbon. Everything on glucose can be compressed into one reaction map. Glucose gives N-hexane with HI, oxime with NH2OH, cyanohydrin with HCN, gluconic acid with bromine water, saccharic acid with HNO3, and glucose pentaacetate with acetic anhydride. That reaction map is the quickest way to revise the structure chapter under pressure. If you can move from glucose to each product and explain why it happens, you own the chapter instead of memorizing it.